webinar. Welcome everyone to the QDesignOptimizer webinar today on April 25, 2025 at 3 p.m. Gothenburg time. I'm super excited to have more than 30 people here on the call who are interested in our work that would like to show you during some interactive session. I hope it's going to be fun. So what is this webinar? I think I need to share my screen again. Is this correct?
We can see the welcome to the.
You can see the welcome, yeah. Okay. Because my Zoom just acted up for a second. Okay, so today we want to speak about the QDesignOptimizer, which is a Python package that allows you and an algorithm that allows you to do automatic multi-parameter design optimizations for superconducting devices, primarily in its current state. And during today's webinar, we would like to introduce the algorithm, discuss the implementation in the Python package, and then during a breakout room session, show you a little bit how to use this package in your own research. And why so? We think that this QDesignOptimizer, which we use in our lab for our day-to-day business, is also useful to you. We want to make it available to you and help you generate complex superconducting circuits. So that's our goal for today for the next 1-2 hours. And we'll have a look at the schedule. So we'll start with a quick Qiskit Metal ANSYS HFSS 101. For those of you who are maybe not super familiar with these two software packages, because they are essential building block for what comes after. So in about 10 minutes or so, we will start looking at the core of the QDesignOptimizer. And this presentation is held by Axel, who's then taking over. We'll have time throughout the presentation to take questions, but if there are more questions afterwards, we'll take a Q&A session at about 3:50 this afternoon. And from there on, we split into breakout rooms and invite you to join us for a more in-depth discussion on an intermediate, beginner, or advanced level to really look at the examples that we've prepared for you, really dive into them and have a code along. Or if you are advanced and you have your own design that you would like to parameterize, they'd be happy to assist you with that in a discussion. This is the menu for the afternoon. And before we start, I want to really shout out this amazing team effort that went into the package. Together with Axel, who's here on the call, I'll point at him with a little pointer here, so you know who to look for. So Axel was part of the team, Pietro was part of the team, Kunal, Linus, Niranian here, and Harsh. We all together put in a couple of hours or a bunch of hours to not just develop the algorithm further, but also to write it up and make it available to you. And this is all work done here in Sweden at the University of Chalmers, under the supervision of Simone Gasparinetti, who is leading here the 202Q-lab, working on superconducting circuits, both on the computational side, but also looking into fundamental research on quantum thermodynamics. Now, let's look at the quantum design optimizer briefly. When you design quantum circuits, you typically have a concept in mind, a Hamiltonian that you want to realize. It may be a fluxonium qubit or a transmon qubit, of which you know the Hamiltonian, you know some parameters like EJ, EC, and so on. From there on, you probably, in a typical design flow, sketch a design which might or might not be done with Qiskit Metal, but here in our implementation, we suggest Qiskit Metal. From there on, we typically run some elaborate high-fidelity precision simulations, eigenmode simulations, or capacitance simulations to predict the performance of the circuit that we drew just before. And then we check how well the simulated values correspond to the Hamiltonian parameters. And based on the comparison, we update the design parameters. So for example, the length of the resonator accordingly to move our target parameter or our parameter from the simulation closer to a target. And in order to run through this workflow of the design of superconducting circuits, many people in the field rely on the design and renderer package Qiskit Metal, prepared by Slatko Minev and IBM. And this package integrates ANSYS HFSS. So that we all know what this is about, I'll give you a quick 101 before we have the optimizer deep dive and look at how to integrate this optimization in an automated fashion. If we speak about Qiskit Metal, most of you might know it. For those who don't, this is an open source design framework developed about 4 or 5 years ago, and it interconnects the design of superconducting circuits and their analysis. Alternative implementations you might be familiar with are GDS Factory, KQ circuits, and others. The idea is that you turn a concept or a Hamiltonian into a design by specifying its parameters. And this design can then either be rendered into a GDS file that is used for the fabrication in your clean room or sent to some foundry, or instead you can render the design into some of your favorite simulation packages. The most standard one, as I said before, is HFSS. And here you can run a bunch of more detailed simulations, for example, eigenmode simulations, capacitance simulations, and they both feed, for example, energy participation ratio analysis that then allows you to compute nonlinear coupling parameters in your superconducting circuit. This open source package is available and pip installable, as you can see here. If we go one step further, I quickly want to show you how this design in Qiskit Metal manifests and what it takes to generate such a design conceptually. So say we are interested in building such a meandered resonator here. Yeah, it's basically a CPW resonator with a starting point here and an end point over there. It has a certain width and a certain gap and a certain length. If we want to generate such a design, we need to initialize Qiskit Metal via the design planner. We might want to instantiate a GUI if we want to see what the design looks like. And then we set a couple of options for this resonator in a dictionary-like fashion, where we specify the position of the input pins here and there. We specify the bend radius for the meandering. We specify the total length. And we will later hear from Axel how to parameterize this in an efficient way. And so while you would naturally expect a number here, this right now appears as a variable, but more on this in a minute. And then we can also specify other parameters such as the trace width and the trace gap, specifying the width and the gap here. And all these parameters, these options as they are called, they are fed into a Q component, which is the route meander, which takes the design that has been initialized here at front, it gets a name, and we pass on the options. Once this is done, we can render or build the GUI, and from there, render a GDS file or move on to simulations and analysis. So this is all about the Qiskit Metal 101. A quick look at what this analysis tool is like that I've been talking about. It is ANSYS HFSS. It's a high-frequency 3D electromagnetic field simulation software. It's a proprietary tool for which you need to pay, but most universities have licenses for it. It comes with a Python interface that is called PyAUDT, also available online, and it builds the interface between Qiskit Metal and this software package. If you look at this software, it opens on a Windows computer, such a beautiful window here. where you specify your project setup, which contains a couple of different elements. It contains the materials and the sheets that you need to specify. For example, the silicon wafer you fabricate on, a vacuum above, and then you specify the metal sheets as 2D structures which compose your circuit. You can see such an implementation here to the right. It's the same implementation that I drew before in Qiskit Metal and then rendered in ANSYS HFSS. It has a rendering resonator, and actually to one side I connected a qubit, and to the other side I connected a transmission line, which could have been rendered in a very similar way. One thing that is very important for the analysis is the specification of a mesh, and the other thing is the analysis setup. When we speak about the mesh is generated in an adaptive way over multiple passes, and this is done in such a way that there's the finest mesh at the points of the maximal field distribution. And so this mesh is regenerated during every iteration of this design process. We can also look at the mode distribution once the simulation is done, and we can identify where in the circuit a mode specifically lives by looking at the field distribution. For example, here I'm specifically looking at the mode that lives in the split transmon here. Alternatively, I could have also looked at the mode that lives in the resonator. We see both modes and their convergence in the result plots, frequency versus the number of passes this optimization underwent. And you can see that towards the end, after 5 passes, the frequency has almost converged and is not changing much more against a finer mesh. And this is about everything there's to know about ANSYS HFSS. And so if we take these tools together, we can generally optimize our superconducting circuits. But so far, it often still relies on manual intervention. And how to automate this is part of Axel's talk, who's now taking over, and talks about the QDesignOptimizer implementation. I just saw that there appeared a message, which is, this means you manually have to feed material properties to HFSS once you render. Yeah, you can manually feed these material properties forward, but you can also specify them during the rendering phase and pass them automatically onto the renderer. So this can also be automated. Yes, Niranjan also answered this question straight away. Are there any more questions regarding this first part? If not, then let's move on with the core part of this webinar. And we move on to Axel.
All right, thank you so much. I just requested access to the screen. And let's get started. So can you see the full screen now?
Yes, I do see the screen. I think that applies to everyone else as well.
And you can see the laser pointer. Great. So, okay, so my name is Axel Eriksson, and I will talk a little bit more about the details of the QDesignOptimizer. So as Lucas said, it is a quite general mathematical optimizer, but we will do it in the specific case of superconducting circuits, and we are integrating explicitly with Qiskit Metal, as it's a very nice match with that. And just to rephrase the general idea, so you are at the task of that you want to have a device with some specific properties. Typically, these can be Hamiltonian properties. This could be some dissipative or general and nonlinear dynamics that you want to achieve. And the task typically starts with that you put down some kind of design that is somewhat close to the design that can actually realize these parameters. But if you would fabricate your first guess, typically the fabricated device will be quite off in the properties. And then what you do is that you sit in this very tedious manual process of running optimizations and trying to fine-tune your device such that you end up with a device that if you fabricate it, you would actually have a device that fulfills this criteria of which parameters you want to realize. And the purpose of this QDesignOptimizer is really to help the manual effort here and to automate quite a lot of it. And that's what this whole package is about. And here you can see an overview over what you need to do to be able to use the package and how it works. So it basically consists of three different parts. One part is about problem formulation. So you need to specify what kind of problem is to be solved. One part is about optimization, how to actually update the design such that you reach the design that can realize the parameters. And one part that is about the validation, like looking at that the conversions has been appropriate and that you have the right modes and so on. So if we start to talk about the problem formulation, you basically have to specify three different parts. The first part is the system parameters that you want to have targets for. So it's basically, for example, the Hamiltonian parameters. You want to have specific frequencies and harmonicities and so on. So these are the goal, the parameters. Then you need to think about, okay, how can I modify this device such that I can really realize and achieve the parameters that I want? For example, to achieve the right frequency of the resonator, you could change the length. So the length could be a good variable to change or the width of the capacitive pad could change the anharmonicity, for example. And you need basically to find one design variable for each target parameter that you have. And what then is a little bit special about this package is that we have made it possible for the user to provide physical understanding of the device, which will speed up the optimization quite a lot. And this is basically then just mimicking the manual process that you would do as a user. So just to take an example here is that if you, for example, would like to have a target for the frequency of the qubit, you know that, okay, you can actually change the design value for the inductance of the Josephson junction, and thereby you can change the frequency. So if you just find the right value for the inductance, you will be able to hit the right frequency. And I will show a bit more in detail later how you can actually specify these kind of non-linear relationships between the parameters and the design variables. But this will help us to speed up and make it very efficient. And we'll discuss it more in detail later. But so it's basically setting up what do you want to achieve, what kind of variables can you change such that you can achieve this, and then specifying how are these actually related. The next part is the optimization itself. So when you have put down some initial guess values for the design, the task now comes to how to update these values such that we return or come into this final design. So it basically starts by that you take whatever initial guess you have and you run a HFSS simulation, which basically then will tell you what parameters you end up with. And then the next step is to figure out how should you update your design variables in the most clever way, such that you get closer and closer to the target. And I will, in a few slides, describe more how that is done. But this is basically the idea that you have an iterative process such that you get closer and closer to the target by using this nonlinear model that you have specified. And you run this a couple of turns automatically. And then whenever it's done, you can then do a manual inspection. Have you converged correctly? Are the mode shapes as they should? And is the general design as you want it to be? So now let's look into a little bit of the details of each of these blocks. And basically to set up the problem correctly, you more or less have to create a table that looks something like this. So you have a design, and then you think about, okay, what are the parameters that you want to optimize for? For example, it could be the resonator frequency, qubit frequency, anharmonicity of the qubit, the dispersive shift between the two modes, and maybe the kappa of the readout resonator. And then you would have to specify, okay, what are actually the target values for these parameters. So you would create a file looking like this, where you specify that, okay, the resonator frequency, you want to be 6 gigahertz and so on. And you can also specify nonlinear elements. So this is the self curve or the anomalistic of the qubit. This is a cross curve or a chi between a qubit and a resonator. And then you have to start to look into this design and think about, okay, what design variables can you change such that you can reach these target parameters? And it could, for example, look like this. So we'll look on the design variables now. So for example, to change the frequency, we already said that we can change the length of the resonator. To change the anomalisticity, we can change the width because that determines the capacitance and so forth. And we will create one file where we specify all these design variables and specify some initial guess for an initial design. And then you also have to use the same variable names here when you construct the Qiskit Metal design. So as Lucas already told you, when you're creating the Qiskit Metal design, you use these different classes that are the predefined components, and they can take different options. So instead of just hard coding the pad width, for example, to be 400 micrometers, you could instead say that, okay, this should actually be this design variable that we can adaptively change as the optimization runs. So we have now introduced the design variable and give it an initial guess. And we have also specified how the design depend on this design variable. And the next thing we have to do to digest this table here is to create something called an optimization target, which is basically defining one of the rows in this table. So the optimization target basically says that, okay, for the qubit frequency, I know that this is a quite good approximate expression for how the qubit depends on the design variables. And I also specify that the main design variable that we will use to reach this target is the inductance of the qubit. And this is basically just an additional information to do some bookkeeping to make sure that we have the same number of design variables that we have parameters, such that we don't have an overconstrained problem. And we're actually a bit more general than this. So these proportionality functions does not only or cannot only depend on the design variables, but in principle they can also depend on other parameters. So for example, in principle, we could write an expression that where the qubit frequency we also expect it to depend on the qubit anomalisticity. Maybe that wouldn't make too much of a sense, but for example, the dispersive shifts typically also is well formulated on this kind of way, where it also depends on the frequencies and the harmonicity. So it also depends on the other parameters. And we're fully capable of writing these expressions in this way. And we can very, very easily change how this expression look like, and it will automatically be picked up by the optimizer and optimized for. So it's you basically have to set up the problem, you basically have to provide this kind of information. And then you will create one such optimization target for each row here. So basically then, to create a new row in this table, what you have to do is these red boxes. You have to add the new target parameter in the targets. You have to add a new design variable that should reach that target. You have to add this design variable in the design such that the design depends and varies with the design variable. And you also have to add such an optimization target and specify how it depends on the design variable, and also specify which of the targets have this design variable as the main parameter. And that's how you can add or remove things from this table, basically. So this is how you set up the full problem. And then we can move on to the optimization step itself. So the first step, as I said, is just information collection. So basically, we will take whatever design variables that we have as the initial guess, and we'll run HFSS eigenmode simulation or capacitance simulation, and combine it with EPR analysis, which provides information about the nonlinearities. And this then basically tell us the information for these design variables that we have set, what will the actual parameters look like. And usually when you do this for the first time, you will not really come on target of the parameters. You will usually be somewhat off. And then if you would do this optimization manually, it would typically look something like this. So the next step is then how to update the design variables. And just to take an example, it would look like this for the qubit frequency, for example. So manually, the process goes like this, that you know that, okay, the frequency is proportional to the inverse square root of the junction inductance. That's a quite good approximation of the physics. So if you would say that, okay, I have an initial guess that I need 10 nanohenry for the inductance, you run the simulation, ended up with 5 gigahertz. And then you say that, okay, 5 gigahertz is a bit off from my target frequency here. That was 4 gigahertz. And manually what you would do is that you would just say that, okay, since I know this expression, I actually know how to formulate an equation such that I can update the inductance value, which will basically be this equation that you solve, which is basically the ratio between the inductances with this proportionality square root of expression. And one way to view this is that since this is the full expression with the constant there, since you have run the simulation at 10 nanohenry, you know that this actually corresponds very closely to 5 gigahertz. So this would basically cancel out. And then you have the full expression, and whatever LJJ solves that equation is the proper LJJ that you need. And another way to view it is just, okay, you don't really need to care about these constants before there because it's just the relative difference between these two. So if you would solve this equation, maybe you do it manually on paper and pen, with pen and paper, and you would end up with 15.6 nanohenry. And if you would simulate that once more, you would get very close to 4 gigahertz. And basically what this optimizer does is exactly the same thing, but just in an automatic way. So if we look at this expression, it basically says here that to get from our current position, so we have some value for the parameter, to get to the target parameter, what we should do is that we should divide by this expression evaluated at the current position. So what are the current parameters and what are the current design variables? And we should multiply by the same expression evaluated at the target. So evaluated at the target parameters. And then if we solve this equation for the x for all the different parameter I, then we would find whatever design variables will fulfill this equation such that we will actually get the target parameters. So it's basically just this expression here, but a little bit more general because now we can also allow it to depend on the other parameters itself. So one way to visualize this is in this plot here. So what we do is that we start with some initial guess, we run a simulation and end up at this curve here, which is basically the ground truth of the simulation results. And then we said, okay, we would like to change the x such that we actually end up with it at the target here. So what we do is that we take this equation here and we plot the model here as well. So the model is basically this expression, whatever value we're currently at, we divide by the proportionality evaluated at the current position, we multiply by this evaluated at the target, and then we have the x's as the free variables that we want to optimize. So we evaluate this x and we see that, okay, whenever we reach this value of x, we should reach the target. So we run another simulation and we see that, okay, this model is actually not spot on. We're actually having just an approximate expression. So we will end up here instead for this x value. But now we have a parameter value that is closer to target, and we can do the same thing again. We again evaluate now at the new position of the parameter divided by the proportionality at the current position, multiply by the expression at the target position, and we will get closer and closer to the target. And we could also see that this model in the first place here, it is quite off. I mean, it's 30–40% off. And anyway, we're very, very quickly converging towards the target in just a few iterations. So this is what the optimizer does. And it also then automatically solves this full nonlinear model that we provide. It's very easy for us to just change the expressions, what they look like, and it can also actually handle the situation where one parameter depends on the other parameters and not only on the design variables. Maybe a small note here is also that this model doesn't necessarily have to cross this point here because the target, if it depends on the target parameters, that is generally not the case. So if you wonder why it's slightly off here, it's just to emphasize that if the target variables, if it depends on other parameters that are not on target, it will not cross this point here. But this is basically how the optimization works. So very, very quickly, even if the model is quite wrong, we will converge towards the target. And then the final step is about the validation. So we have let it run maybe for 10 passes, 15 passes, and we can see that it very quickly converges, and we can investigate, do the mode shapes look as they should? Is the general design looking okay to us? And then we're basically done with optimization. And again, that is running, this full thing here is run fully automatically. We just need to set up the problem correctly. Just to see some results. So here we have done this. We have 5 different parameters that we want to target. And just to get a feeling, so this took about 6 iterations to converge and was run in about 1 hour on a PC. And this, of course, depends a lot on how accurate you want the results to be, because the more accurate you want to be, the more meshing you need to be, or you need to have, and the longer time it will, of course, take. One note that could also be taken is that usually the kappa estimates or the decay estimates of the modes are quite unstable and unreliable. We are in contact here with ANSYS, and it seems like having a better mesh in the set direction, so out of plane, could help to get more reliable estimates for the kappa. And this slide is just to emphasize that we can really optimize many parameters at the same time. So this is an optimization that was run for 8 parameters at the same time. They converge very fast, and of course that also depends on how good is the model compared to how off are your initial guess and so on. And so, I mean, generally this is a very nonlinear problem, and it actually works quite a lot better than we first thought when we started this project. Okay, so this is some more comments on that. You could also have other types of targets. So we could also run capacitance studies. So before we said that we can have eigenmode simulations that could basically simulate frequencies and kappas, and the EPR analysis would help us with the nonlinearities, the curves and cross curves. But we can also run these capacitance matrix simulations that which allows us to also set that maybe, for example, we want the capacitance between this pad and that pad to take a specific value. So we can also have these targets. And we could also have a target for for example, charge line limited T1 decay. So if you have this qubit, you have a charge line nearby, the capacitive coupling will make the excitation in the qubit leak out into the charge line. And we have an explicit target type where you can study that. So this is just to show that, okay, we can also run the capacitance matrix simulations, and we can optimize towards this limit that we want to specify. And we can also do the same if we want to have a capacitance target. So for example, maybe we want the explicit capacitance between the resonator and the transmission line to take a specific value. We can also have targets that are directly targeting the capacitance and not only like the decay rate, for example. So we have started to use this in chips that we produce here at Chalmers, and this is just to show that it seems to work quite well. So we have a 12-mode chip here. Of course, it will depend on how long do you run the simulations, how accurate are the simulations. Here you can see that the qubit frequencies are quite off, which is actually coming from that we have a calibration in this fabrication round that was slightly off, which means that the outcome of the inductances was not as the simulated ones. But generally it works quite well. And I mean, this is just, it doesn't really matter do you use this optimizer or not. This just matters or comes down to how accurate is your HFSS simulation compared to your actual fabrication and the outcome there. So it doesn't matter if you would have done this manually or you would have used our optimizer. And also I mentioned that the kappa estimates are usually quite crude. It seems to work quite well if we just have isolated resonators. Basically, what we do there is that we don't use the eigenmode simulation results, but instead we do a capacitance matrix simulation, and we use a simple expression to instead calculate the kappa. And it seems to agree quite well when you just have an isolated resonator. So now I will just briefly comment on how it would look like if you would like to execute this kind of code. So you will have to specify a bunch of user files, and the heart of it is basically the main.py file. So I will, in the next slide here, go through what are the main parts in this file and how does it connect to the other files that you need to create. So it typically starts with that you define a chip, and you are retrieved with the Qiskit Metal design object and the GUI object for the Qiskit Metal. So this is done in a chip initialization.py file, which automatically loads the design variables that you have specified. So this is actually a JSON file where you have defined this as we discussed in the setup. The next part is that we define something called a mini study. And the reason to choose this name is that usually if you have a quite large quantum chip, it turns out that it's quite difficult to just brute force the quantum mechanics of it on a classical computer. So usually you would have to break it down in smaller parts. So and that is for us a mini study. So we do a mini study looking in these modes, looking in those modes, and so on. And you optimize these individually in different kinds of constellations. And this mini study then basically it takes some arguments here. That is a list of names of the Qiskit components. So all these components in the Qiskit design have different names. So you would basically specify, okay, I want this component and that component, for example. So this is basically a list of these component names, of the Qiskit Metal names. And then you have to specify how many modes do you want to simulate. So here we have want to simulate 2 modes. And you also have to order these modes in the same way as they will appear in the HFSS simulation. So you should start by specifying the lowest mode and then higher and higher modes in frequency. And this order needs to be the same as the order of the targets and also as the order that the HFSS simulation actually turns out to be. So if you start in a position where qubit 2 is actually the lowest in frequency, the framework will confuse these 2 modes. So you need to start in an initial state such that they have the right order. And then there's also, and usually you wouldn't specify these things in the main file. You will usually define this in a mini studies.py file. And you will also usually use a names.py file to help you construct the Qiskit component names and the mode names and so on. The next part is that you would specify the optimization targets. So you would have a file like this and actually import these objects from this file, where you again then will specify for the qubit frequency, you have this proportionality function, this is the design variable. And then you will define as many targets as you want, basically which are the parameters that you want to optimize for at the moment. And then you also define a design analysis state. So it basically just takes in the Qiskit Metal object. It takes one function that you have defined in design.py file, which is basically just the whole construction of the design. So the options and the actual creation of the Qiskit classes or instances of the classes. And also it also takes the parameter targets. So there's a parameter target.py file where you have specified all the target parameters. And the next thing you do in the main is basically to take these 3 different objects and you plug them into the design analysis. And then you can take and iterate over the design analysis and run, for example, here 10 iterations in this loop. So this will basically run the optimization, update the design variables, run it again 10 times. And you can also use this screenshot function to see how your design is developing in each of the iterations. So this is basically the main parts on how they relate to all these other files that you need to specify the information in. There's one more setting that could be interesting here. That is a plot settings.py file where you also can tailor make your plots that are automatically generated. So it's an easy way of how to just configure some settings such that you create these nice plots. And at first, you might think that, okay, this looks like quite many files and it looks quite cumbersome to get onboarded. There is, of course, a learning curve, but we would like to emphasize that this is really just automating the manual work that you anyway have to do. I mean, you anyway have to specify what are targets, how do you change the design variables. You might not call them design variables, and you might not have the structured way of programming it. You might instead have something in your mind, something you do on pen and paper, and something you do in code. So here we do it fully automatic, but it basically take the same kind of information that you anyway have to work with and just structure it in an automatic way. Two more things to point out here is that we have one setting here that is called an adjustment rate, which can make the updates more robust. So that is even if you have, or if you have very crude nonlinear relationships in the optimization targets, so you don't really know how they change the behavior, you could set down this rate to maybe, for example, 0.6, like 60% update rate or something, which basically means a low pass filter or a learning rate such that you don't take as large steps in the design variables. So that makes it slower, but it makes it more robust. And one way to make it faster is to here adaptively change the number of passes in the HFSS simulation, which is typically the very slowest part, saying that, okay, for example, start with just 8 passes, which give a very crude estimate, and then as this loop runs, add more and more passes to get a more and more finely meshed result, such that when you get closer and closer to the actual target, you zoom in and you really spend your simulation time there. So this will make the whole thing faster. One last slide is just discussing the difficulties a little bit. Sometimes you might run into that the optimization looks like this. There's just this jumping around of the different parameter values, which can happen if there is like a strong side effect where the different parameters affect each other, and you don't capture this well in the model. So either you could spend more time on refining your model, or you could, for example, use this adjustment rate and set down this adjustment rate. And I mean, here, this is a little bit misleading example, but usually it would instead look like an exponential trend like this, where you can dampen out this strong crosstalk between the different optimization problems that's basically is running. So you basically can choose here, do you want to spend your time on refining your model, or do you want to spend your time on setting down the other adjustment rate, just let the simulation run for longer and drink more coffee. Some other tips are to make the design variables predictable. So when you decide of how, for example, here to determine the capacitance between the qubit and this pad here, you could either have the width of it as the design variable, or you could have the gap, for example, as the design variable. And usually it would be better to have the width, because that's a more controllable, more directly linear relationship between the capacitance and these objects compared to if you would take the gap, which varies in a more cumbersome way. So depending on how you choose your design variables, you can make it easier or more difficult to write down proper and robust expressions. And the second part is to make the design variables independent, such that if you change this variable, it's much better if that only directly have a strong effect on the parameter that you want to adjust, and not side effects on other parameters. And this also a bit boils down to that it's much easier to solve 5 independent problems in 1 dimension instead of solving 1 problem in 5 dimensions, for example. And this helps actually both when we run the optimization and the solving of the nonlinear model, but also generally the whole construction of how to write a good model. So both solving the model and writing a good model, it helps if you make them independent, or as independent as possible. And also, if you don't really have a clue of how to change something, you could also investigate these nonlinear dependencies. And this is an example of how you could do it. So if you, for example, hard code and say that I don't want to optimize the width of the qubit, but I want to investigate what happens if I change it from 50 to 300 micrometer. And then you can just put this for loop, and you can say that each next optimization step should instead use my hard-coded value and not use the calculated value from the model. And then you will basically see a trend, and you can see, okay, approximately what does this nonlinear dependency look like, and then you can try to write an expression that captures that dependency. And some of the main failure modes that you might want to look out for is these two. So one part could be that the Qiskit component starts to overlap. So for example, if it automatically is trying to adjust the length of this resonator, it might happen that it accidentally crosses and it goes into the gap pocket of the transpond, which completely changes the behavior of the CPW. So that is something that you would like to watch out for. And that you could also do since we have this screenshots. So each time it's done with one iteration, it will take a screenshot of the design, and you can manually investigate it as it is running if you want to. And the next part is that it might confuse the order of the modes. So for example, if you start in a setting where you have one resonator and one qubit, for example, and you change the design variables such that the frequencies of these two is actually flipping, such that the resonator goes below the qubit when it should be the other way. Then it will also start to confuse which mode is which, because it is assuming that the mode order is correct. So that is also something that you might want to look out for. So typically, when I use it, if I want my resonator to be above the qubit, I usually put an inductance such that I push down the qubit quite a lot, and I push up the resonator quite a lot to make sure that they have the right order. So that's basically what I wanted to tell. We will have a bit of questions now, but the next part of the webinar will be these breakout rooms. So we'll have 3 different rooms, one for beginners, where there will basically be another walkthrough of the optimizer and the examples that we have in the online repository. There will be an intermediate group in room 2, where there will be a little bit more deep dive into the examples, and you will also be able to try out the examples in a code along. And then we'll have one room which is a little bit more advanced. Maybe you have already had the time to check the optimizer and you really have a design that you want to use this for. So we will be in that room trying to help you to set up all the different files that you need and try to get you started. And also answer, I will be in this room, so I will also be able to there answer any kinds of questions. And so it will be a bit of a question and support channel. But maybe there are some general questions. Lucas, could you please read them if there are any, or you can also speak up.
So yeah, thanks Axel for this talk. I think it gave a good overview, in my opinion, of the algorithm and the implementation. One question that came up in the chat was on the parameter dependencies. Maybe you can highlight once more in the last few slides how to go about these interdependencies and how to extract the functional dependencies if there are if parameters are not completely decoupled. I think you already mentioned it, but I think maybe you can highlight this once more. The question, I can also read it out, reads as follows. Does this also handle variable parameter that have interdependencies? Like once we tweak capacitive coupling between resonator and qubit, for example, the qubit EC would be different and needs to be retuned. How to go about this? Or in other words, is it like we need to know the functional dependencies on both parameters, etc.? So what do we do with these parameter interdependencies and how do we treat them best?
Yeah, so I mean, it will be fully general in that sense. So here we don't have an example of a capacitance, but in principle, we could add one more line here where we have a capacitance between two components. So that will now be a new parameter. And we could then also specify in our relationship that this, for example, also depends on the value of this capacitance. So it could, for example, be square root of this capacitance here. So it would, if I go maybe up to this slide, here. So here we would then, here we took a dependency towards this parameter, which is a nonlinear parameter, but this could instead be a parameter of this capacitance type. So then it will say param underscore capacitance and identify the two names. And then you have made your expression depending on this parameter. So as that is changing because of another optimization target, it will be automatically taken into account here. So it will really, whatever model you specify that depends on any of the parameters or any of the design variables, it will solve the whole thing for you automatically and just run. And then of course you can write expressions here that messes things up, that is not monotonic and that has multiple solutions and can break for whatever reasons. But as long as you have a design that is predictable, and that this comes back to that tip I had, that make the design predictable such that you actually can write these monotonic expressions, and then you can basically have any connectivity between the parameters and they can be cross-talking as how much you want. But that is fully possible, yeah.
Are there any more questions? This is the moment. Uh, yeah, we have one more question here from Lee Y. Does this also handle the inductive coupling between fluxonium qubits and resonators? For example, if I set the share inductance, then I know the coupling. What do we do with inductive couplings?
Maybe you would be even better to. I didn't fully understand the question. Could you please repeat it? So if you have an inductive coupling and then.
Mm, I think the question is on the inductive coupling between a fluxonium qubit and a resonator via shared inductance. Can you
Yeah, I
can
mean,
you tell how the coupling would
as
be
long as you would
implemented there?
have, as long as you have a way to run a simulation or in any other way predict what the parameter will look like. So now if we have a capacitance, or sorry, a coupling here that is not this capacitive coupling, if it would be an inductive coupling instead, as long as you have a way to simulate and extract that inductive coupling, the framework itself will be able to handle it. We don't have, as of today, an integrated target type that is an inductive coupling. So that is not in place today, but it would be very easy to extend the types of targets to also handle inductive couplings. What we need to do basically is to have a way to, from any of the simulation results, extract this inductive coupling. So for example, run some magnetic simulation where you can get this coupling. So as long as we integrate that, it will be fully compatible with the rest. But we don't. We today we only have the capacitive coupling integrated as a target type, but we could also extend it to an inductive. But that's not in place today. But in principle, it's definitely possible and not too difficult to do, as long as you have a simulation that could actually provide you with the value itself.
One thing that I see there is possible is that you base it on eigenmode simulations, compute the two modes for the resonator and the fluxonium, and then I look at the EPR analysis. I think that should still allow you to compute a chi.
Okay, that could be another way.
Yeah. But I think this would be also an interesting question to discuss further. Maybe look at your implementation during the breakout room session. Thanks for the question. Are there more questions?
And if it boils down to that, you can actually, if you're not interested by the inductive coupling and the inductance value itself, but by the chi, for example, then as Lucas said, then it's already supported because then it just comes out from the EPR analysis.
I actually have a relevant question, I think. Do you think it's possible to extract the transmissions, or like, I should say more like S parameters, by defining some ports? For example, in this case, the inductive coupling case.
Yeah,
Uh, if we extract the touchstone file, and we can potentially interpret it as an inductor, and then extract the inductance, does it allow us to get some kind of transmission matrix out of this, or is it pretty purely an eigenmode simulation, not a driven?
we have been working on also integrating the scattering analysis, and that is also like already provided by the Qiskit Metal repository. So they show how you can run by code scattering analysis using HFSS. We have started to integrate with that, especially when we are interested in the kappa decay, but that is not part of the online repository. We just have that in separate code, but it's definitely possible to also base it on scattering analysis. And in principle, then you could also say that one target should be that the scattering parameter for something should be a specific value, for example. That is not integrated in the online thing, but it's definitely possible. And Qiskit Metal already basically does it for you. So we just need to connect the scattering analysis results and from the simulation pick out such that we map the information correctly to the parameter. So again, it's not in the online repository, but it's definitely possible to extend to it, and we have been working on it.
So basically, there's a hook for in Qiskit Metal for driven simulation already.
Yeah, exactly. Yeah,
Thank you.
and you can already see that in the online examples of the Qiskit Metal. So you can set it up yourself, but it's not yet integrated in our optimizer here.
Thank you. It's clear.
Are there more questions? If this is not the case, then let's move on to the breakout session. Maybe the four leading the breakout sessions could quickly show up with their video streams so that I can introduce you. Et voilà. So here we have Axel, who's leading the discussion in breakout room 3 for the advanced discussion on how to implement and parameterize the QDesignOptimizer in your circuit. Then on the intermediate level, room number 2, we have Niranjan and Pietro walking you through an example in a deep dive. But you also get to code, and you can code along with them if you get the code from the repo, but more on the details in this particular breakout room explained by Niranjan and Pietro. And for the beginners, why beginners doesn't mean you don't know anything, but the beginners means you take it slow and once more. Kunal is walking you through an example step by step that we've prepared for you that shows you a single qubit optimization. And if you want to walk along with us there, then join room number 1. I will now in this moment create the 3 breakout rooms, 1, 2, 3, and 1 again is beginner, 2 is intermediate, and 3 is advanced. And I hope to find many of you there in this breakout room session. Note that I will stop the recording hereafter, and I hope that we'll be able to share this recording with you in some way, such that also people who couldn't make it today find the video stream online. So I create the breakout rooms and hope to find you there. And for everyone who cannot make it into the breakout room session, thanks for joining. And I hope you found this useful. And if you have questions in the future, don't hesitate contacting us. And now the breakout rooms will open.